Hello, this is Dr. Johnson. I'm one of the AP Stats teachers at Capel High School. I want to welcome you to this lesson on chi-square tests for goodness of fit. Chi-square test is applied to a distribution of categorical data. So in this unit, we will be talking about categorical data. And there are three tests in this unit. On today's lesson, we're just going to talk about the first one. Purpose of the first one is to test whether an observed distribution matches a theoretically expected distribution. And this test is called the goodness of fit test. So suppose someone rolls a die 60 times and we get the outcomes that are in the second column there. Now, if you roll it 60 times and the die is fair, then you would expect on average to get 1/6 of the outcomes would be a 1 and 1/6 of the outcomes would be a 2. So the expected count when you roll the die 60 times is that you would get 10, 10, 10 for each of the outcomes. But you can see here that we got considerably more 1s than we expected. We got 16. And we got considerably more 6s than we expected. We got 17 instead of 10. And we got less of the 2, 3, 4, and 5. So the question is, are the dice loaded? This is the data right here. Now, what we could do, we could perform individual significance tests for each value of the die, like we learned in Chapter 9. But this would be inefficient. There is a single test that can be applied to see whether the observed distribution as a whole is significantly different in some way from the stated population distribution. And that test is called the goodness of fit test, the chi-squared goodness of fit. To begin it, we're going to have to write out the null and research hypothesis. The null hypothesis is that all of the proportions are the same and that they are equal to 1 out of 1/6. The alternative hypothesis is that at least one of these proportions is not as specified in the null hypothesis. If one is not as specified, then we know logically that there's going to be at least 2 that are not specified in the null hypothesis. And just as a reminder, hypothesis statements are always about the population, so you should not refer to the sample. And hypothesis statement must include some reference to the context of the problem. Next step is to choose our significance level. There's lots of numbers we could choose. A significance level is a number between 0 and 1, but if we're not told which one to choose, following convention, we will choose the 0.05 significance level. Next step, we need to check the conditions. Chi-square tests can be used to test for a goodness of fit to see whether a single categorical variable has a specified distribution when the following conditions are met. So the first thing we have to check is, does the data come from a well-designed random sample or a randomized experiment? The second condition is the 10% condition. We want to check that when sampling without replacement. And the third, this is the third condition, it's called the large counts condition, but it's different from the large counts condition that we've used before. In the chi-square test for goodness of fit, the large count condition is that all expected counts must be at least 5. All expected counts are at least 5. Now, different textbooks may have slightly different large count conditions, but this is the one that we're going to use. I think it's the one that's most frequently used. What you do not have to do for a chi-square test is show that the sample size is greater than 30, and you also do not have to show that NP is greater than 10, or n times 1 minus p is greater than 10. The large count condition here is that all expected counts must be at least 5. So, what would you do if, when you're checking the conditions, you find out that one of your expected counts is less than 5? A couple things. First thing I would do is I'd go back and I'd check my math to see if I calculated expected counts correctly. It should always be the sample size times the theoretical proportion that you are expecting. After that, if you've checked your math and you still have one of the expected counts less than 5, one alternative is just to say, well, this condition fails, but we will proceed with caution. And this is a wise thing to do, because if they give you a problem like this, the conditions will be met. It's just your job to show that they are met. And if you can't make it work, then move on. Just say that we'll proceed with caution. And there's a third thing that you can do. If the expected counts, if one of the expected counts is not at least 5, then one alternative is that you can combine columns or you can combine rows, and then recalculate the expected counts and see whether with that change you now have all expected counts at least 5. Okay. When the expected counts are all at least 5, the sampling distribution of the chi-squared statistic is modeled well by a chi-squared distribution. A chi-squared distribution is actually a family of density curves that take on only non-negative values and are skewed to the right. So let's take a look at those. Here I have 3 chi-squared distributions. They're all skewed to the right, and they all have non-negative values. They are defined by their degrees of freedom. I'll explain that in a second. As the degrees of freedom increase, the chi-squared distribution becomes more symmetrical. And I think that's all I want to say about this here. The chi-squared test is a one-tailed test, and we're only going to reject the null hypothesis for large values of chi-squared, not for small ones. So next thing we have to do is we have to calculate the chi-squared statistic. Here's our formula for the chi-squared statistic. Chi-squared statistic is a measure of the distance between the observed and the expected counts relative to the expected counts. And this formula right here is on your AP formula sheet, so you don't have to memorize it. Sometimes you'll see it written as O minus E squared, all divided by E. And then with the summation symbol means that we're going to sum over all of the categories. On this slide, I describe in words each of the steps that we would follow if we were going to calculate the chi-squared by hand. But I'm actually going to show you on this slide how to do it. So the first 2 columns are the columns that you've already seen, the value of the die and the observed. Then we have to calculate the expected column. So with the expected column, you take the sample size 60 and multiply it by the theoretically expected proportion. 1/6 times 60 is 10. So for each of my expected counts will be 10. And as you remember, the third condition is that all expected counts must be greater than 5, and we have now satisfied that third condition. In the fourth column, I'm going to subtract O minus E. So I'm going to take the observed value and subtract the expected value. In the case of the first row, I have 16 minus 10. It gives me a 6. For my next column, I'm going to take that difference, O minus E, and I'm going to square it. So I take my 6 and I square it. And for my last column, I take that squared difference of O minus E and divide it by E. So I have those numbers right there, 3.6, 2.5, that row of data. And so I'm going to add up the first 6 rows of that last column. And the sum will be my chi-squared statistic. So the calculated chi-squared statistic in this case is 13.6, and that's the symbol chi-squared right there. So a couple things here. All the expected counts do exceed 5, so we satisfy that condition. As I mentioned, chi-squared tests can only be done on actual frequencies and not percentages or proportions. So if the problem gives you percentages or proportions, you are going to have to work back and figure out the actual frequencies, because this analysis is done on actual observed and actual expected counts. Okay, so let's move on. If your sample reflects the expected distribution, then there should be very little difference between the observed counts and the expected counts, and therefore the calculated values making up the sum of chi-squared should be small, and therefore your chi-squared statistic should be small. Large values of chi-squared are evidence against the null hypothesis. So the question is, how do we know whether a particular calculated chi-squared is large enough to reject the null hypothesis? Well, first thing we need to do is calculate our degrees of freedom. In the case of the chi-square goodness of fit test, the number of degrees of freedom is the number of categories minus 1. So in this case, we had the die was a 6-sided die, so we have 6 categories. I subtract 1, and my degrees of freedom is 6 minus 1, or 5. Now, how do we know whether we reject the null hypothesis? Well, the first one should look familiar to you. If the calculated p-value is less than alpha, then we reject the null hypothesis. The p-value is the area to the right of the chi-squared statistic under a density curve of the chi-squared distribution with k minus 1 or n minus 1 degrees of freedom. Another way of deciding whether to reject the null hypothesis is what I've described in the bottom half of the slide. In this, I compare the calculated chi-squared with the critical chi-squared from the chi-squared distribution table. And if the calculated chi-squared statistic exceeds the critical value of the table, then we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. So let's look at a chi-squared statistic, and on this chi-squared distribution, and on this chi-squared distribution, I have drawn a vertical line for the critical chi-squared statistic corresponding with my alpha significance level. And if my calculated chi-squared statistic is greater than the critical chi-squared statistic, that is, my calculated chi-squared is in the shaded region, then I reject the null hypothesis. So a chi-squared statistic that is greater than the calculated, a chi-squared statistic that is greater than my critical chi-squared means I reject the null. So let's look at it from the perspective of a chi-squared distribution table. And this is one of the tables that you will have available to you on the AP exam. So we have 5 degrees of freedom. So I'm going to go across row with degrees of freedom 5. I'm going to go across until I get to my critical value of 0.05. And I see from this table that my critical chi-squared for degrees of freedom 5 and alpha equals 0.05 is 11.07. That's my critical value. And as you remember, my calculated chi-squared was 13. So because my calculated chi-squared is greater than my critical, I reject the null hypothesis. And this table can actually give you some information about my p-value. So if I look at the row with degrees of freedom 5, I see that under my alpha of 0.025, I have 12.8, and under my alpha of 0.01, I have 15.086, and because my calculated chi-squared statistic is between those two critical values, I know that my p-value is between 0.025 and 0.01. Okay, let's move on. So our conclusion is we reject the null hypothesis, and there's 2 bases for doing so, because our p-value was 0.018, which is less than 0.05. That's one way. Or because our calculated chi-squared of 13.6 exceeded the critical chi-square of 11.07. The data is not consistent with the predicted distribution. There is strong evidence that at least 2 of the dice proportions are incorrect. If you reject the null hypothesis, then you're saying that the observed outcomes are inconsistent with the hypothesized outcomes, hypothesized proportions, and sometimes you may be asked to do a contribution analysis. And what that means is that you're going to go back to your calculations on this page and look at your last column. So remember, our chi-squared statistic was 13.6, and I'm going to look at the last column and I can say, see, when the value of the die was 6, I got my largest contribution, and that was 4.9. And my next largest contribution was 3.6. So my contribution analysis would be to say that the outcomes for 1 and 6 gave me my greatest contribution to the chi-square statistic. Okay, so we're going back to this page. So let's do this problem right here. According to the 2000 census, of all U.S. residents aged 20 and older, 19.1% are in their 20s, 21.5% are in their 30s, 21.1% are in their 40s, and so on. So this is the age distribution according to the 2000 census. And we're going to take this as our given hypothesized outcome. The table below, or the table on the right there, shows the age distribution for a sample of U.S. residents aged 20 and older. For this, members of the sample were chosen by randomly dialing landline telephone numbers. So this outcome, the outcome in this table was obtained by randomly dialing landline telephone numbers. And the question is, do these data provide convincing evidence that the age distribution of people who answer landline telephones is not the same as the age distribution from our census? Well, when we give you data like that, the first thing that I want you to do is calculate the expected counts. And oftentimes the best way of doing it is just to create another column, label it expected counts, and fill it in. Now, you're going to I still want you to show how you calculated one of them. So how did I calculate one? Well, I have, in my census, I have 19.1% in their 20s. So I take that percent and I multiply it by the sample size, 1048, and I get 200.168, and that gave me my expected count. And I do that for all of my other count categories. The first thing I can see is that all of my expected counts are greater than or equal to 5, so we've passed the third condition. But let's go back to the question. Do these data provide convincing evidence that the age distribution for people who answer landline phones is not the same as the age distribution from our census? Okay, so the first thing we want to do is identify. We want to perform a test of the following hypotheses using alpha equals 0.05. The problem did not give us a significance level, so we're going to choose alpha equals 0.05. My null hypothesis is that the proportion between 20 and 29 is 0.191. The proportion between 30 and 39 is 0.215. In essence, all of the proportions given that I've highlighted in yellow up there. And I have to have some reference to the context of the problem, so I say where PI is the proportion of people who answer landline telephone surveys in age group I. The alternative is that at least one of these proportions is not as specified in the null hypothesis. So that's my null and alternative hypothesis. Conditions. The name of this test is a chi-square test for goodness of fit, so that's what I want you to use in the first line. The random condition, the data came from a random sample of US residents who answer landline telephones, so we've met that condition. Independent, because we are sampling without replacement, there must be 10 times 1048 or 10,480 US residents age 20 or older, and this seems reasonable, so we've passed that test. Now we have to check the large count condition. I've done it again here, but if you calculate it in that column, that third column up there, that'll also meet the requirement that you've tested that condition. But you do have to say all expected counts are at least 5, and oftentimes it's good to say the smallest is, and then give me the smallest value. So all of these conditions are met. Now we go to our calculator. This one's going to be a little bit different, so I'm going to walk you through this one. So go to menu 2, the stats menu, click on test. That's the soft menu F3. What type of test? This is a chi-squared test, so hit F3. And now we have to do, we choose the goodness of fit, or GOF. Once we hit that, we are going to be prompted for the observed list and the expected list. So at this point, what you're going to have to do is on your calculator, I want you to input the observed data in list 1 and the expected data in list 2. And it's going to, and the calculator procedure is going to use the data in list 1 and list 2. You have to tell the calculator the degrees of freedom, and since I have 5 categories, I take 5 minus 1 gives me degrees of freedom 4, and when you press execute, the calculator will generate the contributions and put them in list 3. So we do all that, we hit execute, and calculator generates these results. It tells me that my calculated chi-squared statistic is 48.17. That is really big, which tells me there's a large difference between the observed outcomes and the expected outcomes. Tells me the corresponding p-value is a number very close to 0, and the degrees of freedom is 4. So we now have to go up and do our calculations. The chi-squared statistic, here's my formula for chi-squared statistic. I take my O minus my E, square it, divided by E, and really I should do that for 2 of the terms. I just did it for 1 here. Then you do plus ... to represent the rest of the sequence, and then I put 48.2, which was the number I got from my calculator, 48.17. Okay. Now we've got a couple different ways of finishing out because we want to show our work. So you could do it this way, using degrees of freedom 4 and our chi-squared CDF function. You could put the lower boundary of 48.17, upper boundary of some arbitrarily large number, and degrees of freedom 4, and that hit execute will reveal that the probability of getting a chi-squared statistic greater than 48.2 is some very, very, very small number. Another thing you could do is just write that using the calculator's chi-squared test, that's what we did on the previous slide, with degrees of freedom 4, the probability of getting a chi-squared greater than or equal to 48.2 is a number very close to 0. Either one of these would work, but you only need one of them, so just do one of them. Now we have to come to our conclusion. Because the p-value is approximately 0, and that is less than alpha equals 0.05, we reject the null hypothesis. And that means that we have convincing evidence of the alternative, but we have to express that in context. So we say we have convincing evidence that at least one of these proportions of people who answer landline telephone surveys is not as specified in the null hypothesis. And it might be possible that since we rejected the null hypothesis, you might be asked to do a contribution analysis, and that means that you're going to go back to your calculator's result and look at list 3 and look at find what are the largest numbers in list 3. So that's it. Thank you for joining me.